Welcome all to another session on this course on line commutated and PWM rectifiers. And today's discussion will be on flyback converter, the AC-DC part of it. So we are going to talk about a flyback converter which is connected to the AC grid. So if we see the course content and the structure, so we are basically now here. We have in the previous lecture, in the same week, in the previous lecture, we had covered this DC-DC flyback converters in details, and we understood how the isolation works and how are the operating modes of the converter with the switch on and the diode on. Today we will talk in more details about the AC to DC part of the flyback converter and some steady state analysis and equations. And we will also have a small design example, and we will show you some simulation results at the end of the lecture. You can also look into these additional reference material. Now, we have already seen the operation of the DC-DC flyback converter, where we had basically talked about the operation of this part of the circuit, okay, where we had a stiff DC input and we were providing a DC output. Now today we will actually integrate the AC to DC part as shown here. So the AC, in this AC to DC flyback converter, we have the input is the AC grid, and after that, so which is sinusoidal in nature, and after that we have some filters, and then we have a diode bridge rectifier. This is very similar to the boost PFC that we had studied about 1 or 2 weeks back. The boost PFC operation, it is this flyback AC-DC flyback converter is also very similar in operation. Now, when this flyback AC-DC flyback converter is working, we have to remember that the current which is drawn from the grid, that is this current IAC, this current should be sinusoidal. It should be at unity power factor to VAC, and the harmonics on that input grid current should be complying with grid standards like IEC 61000 or IEEE 519. So this gives some additional considerations for the AC grid current, and this is one of the reasons why we have this EMI filter, okay, at the input. This is essential when the flyback converter is working in DCM mode, discontinuous current mode. This DCM operation of the flyback converter is something which is beneficial for the operation of the converter because it can reduce the size. Okay, again, we can see that these AC-DC flyback converters are a lot of times they are used in commercial electronics, for example, TV power supply or something similar. LED drivers. LED drivers are nowadays the one of the biggest applications of AC-DC flyback converter. We will see this LED driver a little bit later in the slides. But yeah, so one of the things that is very popular and mostly used in AC-DC flyback converter is that the converter generally operates in DCM mode. Okay, and just to recall what is discontinuous current mode of conduction, so we have shown you here the inductor currents in CCM, CRCM and DCM. Okay, some of these examples these waveforms you had seen from the boost PFC. I have copied from there, and you can see just to these waveforms are just to give you an example of what is CCM, CRCM, and DCM. In CCM, if you zoom in at this point in the inductor current, you can see that the current goes like this, and the current does not touch zero. Okay, so this is the continuous conduction mode. Whereas in CRCM, what happens is that the current, the instant, at the end of the cycle, switching cycle, the current comes to zero, and again it goes back, hits a top limit, and then comes back again. Okay. The average current is given by this red line, while the peak current is given by this violet line. Okay. So this is what happens in CRCM. Now, when we go to DCM, the inductor current is actually zero before the end of the TS time period. So as you can see here, if you see this part, the inductor current here goes up to a certain value, comes down, okay, and then there is a zero part, okay, and this is the reason why it is called a discontinuous conduction mode. So this is the switching time, switching cycle TS, and D1 out of this switching TS time period, D1 TS, the switch is on, the current rises, and then it falls, and then it is zero. Okay. Now this particular operation of AC-DC flyback converter under DCM has found out, people have explored it, and they have found that this is particularly advantageous for many aspects, which we will see. Note that this average current, okay, here this was the average current, IL average, and here also this dotted line here is also the average current, okay, but the peak current is way more than the average current, right? And if the value of D1 goes smaller and smaller, then this average current will go smaller and smaller. Okay, fine. The average current can also vary. Okay, as you can see here, average current can vary with time. We will talk about it a little bit later. Just to give you a concept of what is CCM, CRCM, and DCM, we have included this slide. Now, the flyback converter, when it operates in DCM, it functions as a natural power factor circuit without any additional control. Okay, and at low power levels, for example, for this kind of LED drivers, where the power level is typically less than 100 watt, at low power levels, this can be a very effective and low cost approach. Okay, one thing that we will see here is that this current, because it is a discontinuous conduction mode, automatically it means that this current here is discontinuous. Whereas we want this current here to be continuous. Okay, so this current must be continuous from the grid point of view, whereas this current here is discontinuous here. Okay, and so we need a form of a filter, okay, so as to remove the harmonic parts from this I in and make the current 50 Hertz sinusoidal. Okay, so the filter basically removes the high frequency harmonics due to the converter switching process. Okay, so this is essential when we operate the DCM flyback converter. Now, one question that we should address now is why the DCM is attractive. Okay, so when I say that a DCM, so you can see here there is as uh, we have extensively talked about in the previous lecture, this transformer has a magnetizing inductance, which is called LM. So when we say DCM, we mean the current through that inductor LM, okay, which we had discussed in the last class. So that current is basically discontinuous. Now, when you operate the flyback and DCM, there are certain plus points and certain minus points. What are the advantages? One of the advantages is that there is a lack of reverse recovery loss. I mean, the diode current here, you will see the operation, but the diode current here will go to zero and then it will turn off. So therefore, there is no reverse recovery loss in the diode. And so there are less losses in it. So this has been reported in many uh, applications that the losses in this DCM operation is lesser as compared to CCM operation. So this is the advantage. But the disadvantage is, as you have noticed here, that from this curve, that the peak current will increase, right? If you go with the DCM operation for the same value of the average current, okay? So as you can compare, like in CCM, the average current is here and the peak current is maybe slightly more than the average current. Whereas in DCM, the average current, the peak current is way more than the average current, right? So uh, that is the problem in the in this converter. So higher peak current will result in so you have to design, right? You have to design your inductor so that it does not saturate, and you have to also take wires such that it can handle that peak current safely. So maybe the wire gauge may increase a little bit. So So, but in spite of this fact, this higher peak current, the overall inductor size actually goes down when you use DCM. Okay, because one of the reasons why the inductor value goes down is simply because of the fact that you are now storing less amount of energy in the inductor, right? In CCM, if you can see the waveform, in CCM, you are continuously storing a lot of energy into the inductor over which there is a ripple, okay, small ripple. So there is a small fluctuation in energy, but overall you are storing a lot of energy into the core of the inductor. On the other hand, in DCM, you are providing some energy, but before the switching cycle ends, you have completely taken out the energy from the inductor. So which means in every switching cycle, the inductor does not need to have a lot of energy to be stored. And so it will actually have a smaller inductor value. But on the other hand, the transformer wire gauges must be higher because you are going to, so you will have thicker wire. So this is something, some plus point. So this is the plus point and this is the minus point. Here also there is a plus point and here there is a minus point. Okay. And one of the important things is that DCM causes discontinuous and large ripple input current. Okay, so we must have additional input filters, right? So this is the minus point here. But overall, if you see all the applications and commercially made flyback AC/DC flyback converter, most of the people, most of the manufacturers and other researchers, they would prefer DCM operation of the flyback converter. And so we will actually learn it in more details about this DCM operation. You will also see that the DCM operation automatically leads to unity power factor. Okay, if we do it intelligently. Okay, so that is also one of the advantages of the this operation. So let us see the AC to DC flyback converter under DCM operation. Now, to if you see here, um, whether it is AC, CCM or DCM, if it has to work as a PFC, okay, the the grid should see that this current which is flowing IAC is like a perfectly in phase component of VAC, which means that the entire converter looking from this left hand side should appear as an equivalent resistance RE. So the DCM should act as a resistive load to the bridge rectifier. Okay. So if you look from this point, we have also talked it in the boost PFC circuit. VG and IG should be in phase. Typically, the VG will be something like this. Okay, VG will be something like this. The average value of IG, the average value should also be something like this, a sinusoidal waveform here. Okay, average value. Instantaneous value will be different. So, yeah. Now, when we talk about the average and the instantaneous value, we will now introduce a notation. The notation is something like this, IGTS. What does this mean? It means that the average value of IG over a switching period. Okay, TS. So for example, here if you see this is the TS period and the average value of IG is here. Okay, so this value will be IG with this subscript and we'll say IGTS. Okay, this is used in many textbooks. So IGTS means this is the average value of IG in this switching cycle. Note that the IGTS is changing in from each switching cycle. So you can see here IGTS is somewhere here and somewhere here in at the lower parts of the AC waveform. Um, so IGTS is IGTS is going on changing, right, at the different parts of the AC cycle. We must also understand that IGTS, IG value will be changing in the peak value. The peak value of IG will change due to loading. Okay, so suppose in the morning the converter is loaded by 100 watts and at the evening the converter is loaded by 10 watts. So then this average value which is shown by the dotted, this average value, this will go up or down. Okay, I mean the peak value of this IGTS will be going up or down. Okay, at the same time in each half switching period, so this period is the AC cycle. Okay, so this is the AC cycle and this will be 10 millisecond because remember we are our VG voltage is something like this. Okay, and this is 10 millisecond if I am taking a 50 hertz signal, input grid signal, and the 50 hertz means this is 20 millisecond. Okay, we are getting a rectified output at the diode bridge rectifier. So our output of the rectifier is having this kind of lobe width of 10 millisecond. Inside that 10 millisecond, we are seeing the discontinuous conduction mode of the flyback converter. So here what I was saying that with loading, the peak value of IGTS will change, but the value of IGTS will also vary from one switching cycle to another switching cycle. Okay, this we have to remember. Now, when we want to do the steady state analysis of this converter, then we can assume that it is being fed from a constant voltage source. Okay, and this is obvious because one must understand that uh, basically our input voltage is something like this, as I was telling. So this is 10 millisecond, and the switching is happening very rapidly inside this 10 millisecond window. So inside this 10 millisecond, the current is going 1 to 0 like this, very rapidly, okay, inside this, right? So we are, this can be like at 100 kilohertz, okay. Um, we can explain it from the next slide, and then I will come back to the previous slide. It is very similar to how the four switching states of a boost PFC circuit operates. Okay, so here if you see, the diode bridge rectifier has two switching states. In one state, these two diagonal diodes are conducting, and in the other state, these two diagonal diodes are conducting, and that is why your VG voltage is something like this. This is the VG voltage. Okay, but the flyback converter here, you can see here, the flyback converter also has two switches, one switch, one diode, S1 and D, and they are actually switching at a very fast, at a much higher frequency than this 50 hertz. Okay, so it may be switching at 100 kilohertz. So therefore, during the positive half cycle of AC, S1 may be on or D may be on. And similarly, during negative half cycle of AC, which becomes a positive half cycle after rectification, again, both two conditions are possible, S1 on and D on. So therefore, the converter has basically four switching states, very similar to what we had studied in a boost PFC, right? So therefore, in this case, we have a very high switching frequency. So let me try to draw it here on this curve. Okay, let me try to draw it in a zoomed fashion. So suppose I take this half cycle of the, okay, and here the current will be going like this, and then DCM, so the zero, then again like this, like this. You can understand how I am drawing the current, okay. Fine, so the average value is here. The average value is here. This is the IG average, okay. Now, yeah, so now, so therefore, what we can see that we can analyze, so this portion, if we analyze it, okay, in that portion, small portion, the input voltage can be considered constant. Okay, if we zoom into this window, okay, in this window, during that portion, the input voltage may be considered constant. So this is what was said here. The analysis, the input of the flyback converter is assumed to be a constant voltage source. Okay, and the following expressions will be obtained, like V0 by Vg, okay, the output by input voltage, and the average input current of the flyback converter. So we will analyze the whole thing at the switching cycle, okay, remembering also that how the overall 100 hertz component actually is coming. Okay, now one of the things that we must keep in mind is that in DCM analysis, the small ripple approximation is not applicable. We had done the small ripple approximation when of the inductor current or the magnetizing current ILM in the CCM mode of operation, right? Where the ripple was very small. But in this case, when you are going for DCM, the ripple can be much, much more. And so in DCM analysis, the small ripple approximation is not applicable. However, the output capacitor is designed to have a small ripple. So delta V0 by V0, the delta V0 by V0 is maybe taken as 1% or 2%. That approximation is still valid. Okay. So with this approximations, with this understanding, and also understanding that there are 4 switching states and there are 2 frequencies involved in this, we now go and write the uh, the equations in one switching cycle. Okay. Now we are considering only one switching cycle. Okay. Right. Okay. If it is 100 kilohertz, this value will be 1 by 100 kilohertz. Okay. Which is about 10 microsecond. Okay. So we are in a very small window out of this 10 millisecond, uh, 10 millisecond overall window. Okay. So this is where we are now, and we are trying to analyze that switching cycle. Now here, what happens? Kindly recall how the converter works. The converter works with the fact that the switch turns on S1, and then the input voltage VG comes across this dot terminal. So the dot terminals keep in mind. And so the on the output, we have Vg by 1 is equal to V2 by N. So therefore, if this voltage is V2 here, the secondary voltage, so V secondary voltage is N times Vg, and along with this V0, the diode here, the diode will get reverse bias. It cannot conduct when S1 is on, right? We have discussed this previously. And so the analysis will exactly proceed with the way that we have done the analysis with the DC-DC flyback converter. The only thing that will now change is the waveform of ILM. Earlier, the ILM waveform was something like this with a very small ripple. Okay, but now it is no longer valid. So we will remove this one, and we will talk about ILM, which is something like this. And you can see here it has a 0 period. Okay. So let us first see what happens when S1 conducts. So we are now in the first D1 TS time period. You can see here we are in the first D1 TS time period. And there we are trying to find out the equations. What is the voltage across this LM? VLM is equal to VG, LMDNM. This is basic equation. During this time, the diode is off. So therefore, this current IC is basically minus V0 by R. And here we have taken that this V output is fairly constant. And then we have this input current IG. This is the current which is coming after the diode bridge rectifier. This is equal to ILM, right? We have taken VG to be constant as we had discussed in the previous slide. A small TS time period where VG can be considered constant. Now, if the switch is on for D1 TS time period, then what will happen is delta IM will be VG putting this into this one. So this becomes delta IM and dt becomes D1 into TS here. And therefore, you can get what is the value of delta IM is equal to Vg into D1 TS divided by LM. And that is what we have written here. Okay, so therefore, what will happen here now, let us see the waveforms. Vg is coming on the VLM and the current is rising, and Ig is equal to ILM. So this is the current here, and IC equal to minus V0 divided by R, right? So these are the waveforms. Now let us take the condition when the diode conducts. As soon as you remove the gate pulse from this switch, it will be turned off. The diode will be getting forward biased, which we had discussed in the previous lecture. And then what happens is this VLM voltage will become minus V0 by N. Why is it so? Because as soon as the diode conducts, and if there is no voltage drop across the diode, this V0, this voltage V0 comes on the secondary here, okay, the same voltage, and then it will get reflected on here by this factor of minus V0 by N, the transformer turns ratio. So this voltage will come on the VLM, and therefore, being a negative voltage, the inductor current ILM will fall. And IG is not flowing because this is, as we discussed last time, this is a current which is representing the uh, decay of the flux in the core. Okay, no primary current will flow, and so this is equal to 0. And during this point, I see, okay, so this current here, this diode current, the diode current will have two components, one going to the capacitor and one going to the load. And the capacitor, so this is the capacitor current, and then this is how it looks like here. And then uh, the capacitor must be replenished during this point of time. It has lost its energy in the previous D1 time period. It had lost here, but it must be replenished, okay, so that the capacitor, average capacitor voltage remains constant. So these are the equations which is present during this time, and you can easily verify these equations. Now, the current that was flowing, that D2 for D2 time period, the inductor current, and then comes to 0 here, and then starts the DCM operation. Okay, the current becomes 0 here. If the current is 0, so it has 0 slope, so therefore VLM is also 0. Okay, so the voltage across the inductor is 0. Of course, IG is not flowing, IG is also 0. And so this is here, and I see the capacitor has to now again supply to the load, okay, because the no energy is now coming from the primary side. The inductor has lost all its stored energy, and so it cannot deliver anything to the capacitor. And so, and of course, both the switches are not conducting. Okay, the capacitor is the only person or only element in the circuit who is still delivering the energy to the load. Okay, all others have exhausted their energies, right? So this is what is happening now. So this is the discontinuous interval. Now, if I want to um, find out what is the input-output voltage relationship, so we know the volt-second balance, and the average voltage across the magnetizing inductor must be 0, right? When the converter is operating in the steady state. So we had Vg, so volt second, so Vg into D1 into Ts is equal to minus V0 by N into D2 into Ts. Okay, this sum of these two must be equal to 0. And so we get V0 equal to N D1 by D2 into Vg. Okay. Now, although we can know what is the time for which the switch D1 has been turned on, because it is under our control, how much time D1 can be turned on. But diode is an uncontrolled device, and so the diode conduction interval D2 is unknown. So we need a second equation to get rid of this D2 here. Okay. And this we can do by seeing the capacitor charge balance. Okay. So in order to see in order to analyze what happens with the capacitor charge balance, we see that this current ID, which is flowing through the diode, this, when the diode is on, is sum of this current and this current, okay, V0 by IC plus V0 by R. Now, one of the things that you must remember is that the capacitor cannot carry any DC, right? So whatever is the DC content, DC inside this diode current, that DC should flow into the resistor, right? So the average value of the diode current in a switching cycle must be equal to the load current. Okay. So the average value of ID, the DC component, so the average value, as we had said, we will be representing average values by this notation. Average in a switching cycle, IDTS. This current must be equal to V0 by R because the capacitor has infinite frequency, infinite impedance at DC. So it cannot carry, right? So therefore, IDTS must be equal to V0 by R. Now, how do we know what is IDTS? Now we have already drawn the diode current, okay, which we have shown in the previous slide. And from there, we know what is the average value of the ID current. In fact, you see here, this is the ID current, which has this peak of ILM peak by N. And we know that the average value of this triangular waveform is half from that half base into altitude, the area under the triangle. And so therefore we can write ID into ID in TS is 1 by TS. Okay, so this is the total time period TS. Okay, so we are trying to get the average value, and then half here ILM peak by N, half into altitude into base. Okay, so we get this value. So therefore, and we also know what is ILM peak, right? ILM peak is basically delta ILM. So this is what the how much the inductor current increased, which is equal to Vg into d1 Ts by Lm. And by substituting these values, what we see is IDTS equal to this value here. Okay, half of this one. And from this, we can find out and from 2, that is from here, this one V0 by R, therefore is equal to half of this one, the equation number 5, right? It's some mathematical manipulations. So we have now two equations. One equation is coming from the inductor volt second balance, this one. And we also have another equation V0 by R equal to half this one in from equation 5. So by manipulating these two equations, and we can eliminate D2, and what we find here is this equation here. Okay, so this is basically the input-output voltage relationship in DCM, operation of the flyback converter. Okay, now here you can understand actually D1, right? D1 has, we will see sometime later, D1 has a term in the turns ratio inside D1. Okay, we will see what is D1, but this is the, so therefore V0 by Vg depends on N. Okay, but we will see, so this is the input output voltage relationship that we obtained in this converter. Okay, now let us see what is the average value of the input current over a switching cycle. Okay, so again, similarly, we can see IGTS, again, do the same thing, right? And we can get this expression here. And then we will see delta ILM, we have found out is like this. And if you substitute, then IGTS is something like this. Okay, this is going to play an important role. We'll see this in next slides, that what is the average value of the input current. Okay, because this gets reflected on the AC side. Okay, this IG current will get reflected on the AC side. Okay, uh, so one of the things that we immediately see is from this equation is that Vg by Ig Ts, okay, Vg by Ig Ts, this factor here, this is equal to 2 Lm by d1 square Ts, right? So um, if we make sure that the D1, okay, when the DCM flyback converter is operating, if we say that with a constant switching period, so if the switching frequency is constant in the converter, so TS becomes constant. LM is constant. We do not want to go into saturation. And if we make sure that the LM has a constant value, and suppose by through a closed loop control, we can ensure that D1 is also constant. Okay, right? If we can make sure, then what happens is this ratio VG by IG in TS becomes directly proportional and is a constant. Okay, what does this mean? It means that whatever is the shape of VG, right? IG will exactly go on following. It is just a proportionality factor. So basically it becomes a resistor. Okay. So remember VG has this waveform. Okay. But in a switching cycle, VG is just a simple straight line here. I mean, a constant value. Okay. And IG in that switching period is basically, because this equation is there, it is basically just following the VG waveform with a proportionality factor. So, so VG is basically this waveform, Vm sine mod sine omega t, like this here. So therefore, IG will also become exactly like this. So IG will become, so let me take a, IG will become something like this with a proportionality factor. Okay, exactly like this. So this becomes IG. Okay. So the DCM flyback converter will act as a natural power factor circuit. Okay, provided all these values here become constant, 2 Lm by d1 square Ts. Okay, so this is one of the advantages of operating this converter under DCM. Okay, so again, now we give it a formal name. We know what we have seen this name, the emulated resistance. The emulated resistance is the resistance seen from here, okay, which will again get reflected and will be seen by the grid. So the emulated resistance, okay, in the previous lecture, we had defined from grid point of view. Here, it's the same thing basically, okay, provided we actually have the lossless filters and everything. So then this RE is equal to VG by IG TS, right? And so RE can be given this value. Okay, we have seen it equation 9, the 2 Lm by d1 squared Ts, and that is exactly what is RE now. So therefore, the DCM flyback converter presents a resistive load to the AC input. Of course, we have here assumed that the EMI filter has no losses and nothing, no drop and everything, which is to a fair degree is a good approximation to start with. Okay. So this is how the converter now works. Okay. But one thing that we must make sure that we are going to work in DCM. Remember that. So therefore, one must select the value of D1 in such a way that, so if you see here, uh, this portion is 1 minus D1 into TS, okay, right? So D2 must be, D2 must be less than 1 minus D1 because we want the current to come back to zero. We want the current to come back to zero at the end of D2, okay? So if this is violated, then the current is not going to come to zero. Means it's going to start and like start again. Okay, this we don't want. So we want to make sure that this D2 time period is less than the available 1 minus D1 time period. Okay. So therefore, we don't want this condition to happen. And so we will say that this is the 1 minus t1 time period. Okay. And d2, this must be less than this 1 minus t1 ts. Okay. And this should hold throughout the AC cycle. Okay. So usually in the control system or in the closed loop control, d1 ts is basically kept constant. So therefore, we can say that d2, and again, we have seen from 6, we have to go back to one of the equation. The expression for d2 is n d1 by v0 into vgt. And so we can find out that d1 should be less than v0. So from the terminal quantities, v0, v output and n and vg, we should say that d1 should be less than this. Okay. But now you can see that VGT, this value is changing, right? The value of VGT is changing. And so if we have to make sure, so remember this ILM current, okay, the ILM current is something like this. Sorry. ILM current is something like this, remember. Okay, so ILM current is going to increase at the peak of the, it maximizes at the peak and then it starts to fall. Okay, so therefore, where is the peak of this ILM current? Right, the ILM current will peak at the peak of the input voltage. So the worst case for this condition to happen is when the rectified sinusoid is equal to its peak value Vm. Okay, because then only the VGT is having its maximum value, right? Even under that condition, even under that condition, DCM should hold true, right? So therefore, D1 should be, so if the VGT put the maximum value, NVM, okay? So V0 by V0 plus NVM, right? So this condition, so if we can ensure this condition is happening, then we have ensured that DCM operation in ILM is always happening throughout all points on the AC line sinusoid. Okay, so then we know what is the value of D1. So we have also found out what is the value of D1. Now, another thing that is important is the selection of the turns ratio N. And this turns ratio is another degree of freedom. Okay, so usually we do not use a very low value of D1 or very high value of D1. We use a moderate value. Okay, and then we have this N in our hand. So a reasonable value of N can be chosen. Okay, and reasonable value of duty cycle can be chosen. And then the N ratio can be adjusted. Okay. Another one is another equation that is of significance is how much is the value of LM. So LM is this one, okay, which we have got from equation number 11. And so we can actually get it like what is the value of RE, because RE is VM square by 2 times P load, because P load and P in are same, which is equal to VM square by 2 RE. We have seen this several times in Boost PFC. And so RE equal to VM square by 2 P load. And so LM can also be written in terms of V1, D1, okay, and P load. And how do you choose the capacitor? And of course, it's the same case presented for the boost PFC. We want to maintain a small ripple in the output voltage. So C equal to P load divided by omega V0 delta V, okay, which we have derived previously. And so this is how we can choose the value of the capacitor. right? So one of the things that you should also keep in mind is that we had also shown it in a previous one, that this voltage across the MOSFET when it is turning off. Okay, so this voltage we have shown it like this. Actually, the voltage is not like this. The voltage across the MOSFET, if you see when it is turning off, when it's turning on, the voltage is zero, but when it is turning off, okay, the voltage across the MOSFET goes like this. Okay, and this is primarily because of the leakage inductances here and here. Okay, because we are basically breaking the IG current, right? And so the leakage inductances of this transformer, the non-ideality, that will give a LDIDT kick on this MOSFET, and therefore this MOSFET must be over-designed. We had seen this in a previous lecture. So we put some over-designing on the voltage rating of the MOSFET, but we can also put snubbers across the MOSFET. So you can see some literatures where these are analyzed in details. So let us take an example, small example of an LED driver. Okay, because I told you the DCM flyback, AC-DC flyback converter under DCM operation is frequently used for LED driving. So let us consider a 600 into 600 LED panel. Usually they have these LEDs made with 2835 package. Okay, suppose we have 75 LED emitters inside that panel. Okay, and the nominal voltage and current of this lamp are something like this. And the power rating is 35.1 watt. We have taken these data from this reference. Okay, you can refer to this paper. Now, electrically, this LED panel is modeled as a series connection of an ideal diode with a threshold voltage of 70.8 volt and a dynamic resistance of 16 ohm. Okay, this is experimentally obtained. Now, what we want here is we want to have a flyback AC-DC converter in DCM, and we want to drive this LED. And the input to the driver is 230 volt, 50 hertz single phase supply. Okay, so this is how the whole circuit looks like. So you have the EMI filter, you have the VAC, this is the flyback converter, and this is the LED panel. And this panel, and so there's a diode, and then there is this resistance and the threshold voltage. Okay, so this is the equivalent circuit. So we can choose the values very quickly. Okay, suppose the flyback converter, we choose the switching frequency of 100 kilohertz, and we take it turns ratio as n equal to 1. Okay, this is just for simplicity. We are just taking an example application. Now, first is we have to find out D1 such that the converter operates in DCM at all points. Okay, so we have got this V0 voltage, 78 volt. We need 78 volt here. Okay, 78 volt, and n equal to 1, and Vm is the input AC voltage, which will be 325. And we have seen this value of D1, one of the equations previously. So we must have D1 less than 0.193 to have it in DCM, right? So then we can choose the value of D1 like we can choose the value of D1 to be like 0.18. Okay, now we have to choose what should be the value of the magnetizing inductance. Okay, uh, assuming that the system is lossless. So Lm is given by this expression Rd into D1 square Ts by 2, and where what is Rd? Rd is Vm squared by load, and so Vm is 325 and load is 35 watt and 2 times this, so then Rd comes out to be 1507 ohm. We have already chosen Fs to be 100 kilohertz, so Ts is equal to 10 microsecond. So all the values are here, and we can find out what is the value of Lm required, and which comes out to be 244 microhenry roughly. Okay, so this is what we get for the value of Lm. And how do you know what is the value of the output capacitor? And we want that LED current peak to peak ripple to be restricted to 45 milliampere. So delta I, this delta I is equal to 45 milliampere. Okay. And so the equivalent resistance of the LED is already obtained from the data sheet of the LED or from experimentally obtained values. So we now know what is delta V. Okay. Delta V is known, P load is known, V0 is known, and so we can just substitute all these values and we get a roughly the value of capacitance to be 2 millifarad. Now, one thing that is important is to design the EMI filter. Okay, uh, which the EMI filter designing is a elaborate process, but we will just quickly design it. Okay, remember that this is the harmonic producing source. Okay, this is the flyback converter here. Okay, this is basically treated as a harmonic producing current source. And so this one here, the resonant, so we have to choose this L and C in such a way that this does not cause the harmonic frequency currents to pass into the grid. Okay, so basically the EMI filter here is such that the switching frequency are attenuated by like 40 dB. Remember, this is a second order filter, so it has a negative slope of 40 dB per decade if you plot the gain magnitude of this filter. Okay, and so it is very easy to design, right? The Z2 by yeah, gain of this filter, and you can put this as the 40 dB required. So basically, if you put the resonant frequency of the filter as 1 by LF and CF, and you put F0, the corner frequency of the filter, to be 10 kilohertz. Basically, you will have this one and it falls like this. So this you have taken 10 kilohertz and this as 100 kilohertz is where your switching frequency comes. So you want so this is falling at 40 dB. Okay, so you want to have a 40 dB attenuation for this 100 kilohertz switching frequency component, which is present here. And we want to completely get rid of it so that nothing glows into the AC side. And you can choose a CF of 100 nanofarad and LF is 2.53 millihenry. Now, sometimes people, so this has a problem, this is perfectly resonant. So which means any switching frequency which coincides with the resonance frequency will have a huge amplification. So sometimes we use a damper. Okay, so damping like this or damping like this, you can use the R of this L, okay, is also acting as a damper. Okay, so we use this kind of circuits also in addition. I'm not going into the details. You can just quickly have an idea from this L and C values. Okay, 100 nanofarad and 2.53 millihenry. So we actually simulated these values, and here you can see that the input AC grid voltage here, and then we have the input AC grid current. Okay, this current, which is actually pretty much sinusoidal. Okay, very nicely shaped, right? And the I in. Okay, so first let us see IG. So you can see here IG, right? And this is basically this type of current. If you will show you the zoomed version, right? Is this current inside, right? And this is the IG current, and note the peak value. Okay, the peak value is going to 2 ampere. Okay, of course, this IG current gets reflected on the input of the diode bridge rectifier as I in, same current, but now you have a positive and negative side here. Okay, uh, but again, I in is having a peak current of more than 2 ampere, whereas you see in IAC the peak current is only like 0.21 ampere or something like that. Okay, why is it so? Because this is happening because you see the average value of the current here is very small. The average is somewhat here. Okay, And the peakiness, you can understand the peakiness, okay, the D1 factor. This is the peakiness, but this is average. So the average value here is like 0.21 or zero point 0.2. This is the peak average value, whereas the peak current here is touching like 2, 2 point something, right? So yeah, so this is important to note. The inductor here, this current, the inductor current in the filter, this is designed with this current. Okay, so it will not be a very big size. The peak current is very low. Okay, right. Yeah, so this is the IG current. You can see here, this IG current is as I was telling. Okay, so this may be the average value, which is slowly, maybe slowly increasing. Okay, because it's part of the AC waveform, right? And so uh, yeah, so this is the average value of the current here. Okay, IG current. Okay, the output voltage here you can see the output voltage and the output current. We are putting a resistive load. Output voltage has a small ripple. Okay, 78 volt, over which there is some maybe 1 volt ripple which we have kept. And output current is something like this. So this actually shows you some of the important waveforms of this converter. And at the end, we will briefly highlight on the closed loop control. And there are several control techniques for this flyback converter in the discontinuous conduction mode. But yeah, there are several techniques. One of the techniques is this average current control. So what do we do here is that um, basically we actually control this output current. Okay, and this output current, so we first find out the variation of this output current with respect to the duty ratio that we are applying here. How does I0 vary when we apply this D1? Okay, and so that gives us the plant transfer function. And after that, we have seen this previously in many of the converters. Yeah, boost PFC we have also seen in the three-phase VSC. So the plant transfer function is first obtained, and then it can be used to design the compensator or tune the compensator gains so that we get adequate bandwidth and something like that. Okay. So what in this case, suppose in the LED driver application, so this is the LED driver application. Here, this current is controlled. Okay, this output current. So we have a reference of this, and of course we have a sense of this. Sense current is basically a voltage. Okay, which comes to this a small series resistor, which is the sense resistor, and you get this voltage corresponding to the current. There is a reference, there is a sense, and then there is a compensator. And the compensator, so we need an isolation here because this side is isolated. You see the ground is isolated, so we have to get it in an optocoupler. Our isolation pulse width modulator goes to the gate driver. Okay, this is very important, the isolation part. Okay, so this compensator output will give us the required value of D1. And so there's an error, and that compensator gives a fixed value of the duty ratio D1, right? Once you have this D1, as you have seen that we have this condition, right? RD equal to 2 LM by D1 square into TS. So we have fixed value of TS. We also have got the D1 from the control system. LM is fixed. So basically we are seeing that we can maintain a constant value of RE through this kind of a closed loop operation. Okay. And we also note that there is no separate control loop for PFC operation. Okay. So no additional control loop is required for the PFC operation. So this is automatically taken care of in the DCM mode of flyback converter. Okay. We just fix the value of D1, and this current here, okay, being forced by this MOSFET to follow D1, this current will automatically follow the VG voltage automatically. Okay. and so it will become sinusoidal, right? So this is how it works in this particular type of LED driver control system. There are other types of control system also. For example, you can have a sensing of this current and control it. So this is the primary peak current control. There is also secondary voltage control. Okay, sometimes people uh, try to control this voltage, secondary side voltage. Of course, if you control from the primary side, then isolation requirement is less because your controller will have a ground which is connected to this point here. Okay, the ground will be common to this one. Whereas if you control from the secondary side, then you need an isolation in between, right? Because your controller will have a different ground as compared to this is isolated, this side, secondary side. So if you sense secondary side quantities, then you must have an isolation in between because your microcontroller or your analog controller is at a different potential. Okay. But if you sense from the primary side, they have the same ground. So this is something that can happen. Okay. So, but yeah, there are several possibilities and one must refer to what type of control uh, one should use. Okay, so we don't want to go into a detailed discussion on the controller because this follows very similar to our understanding and how we develop the control system for the boost PFC. So this is also the flyback converter control system is also similar to it. So this leads us to the end of this session. And therefore, what in summary, what we can see here is that we have, uh, in today's class, we have actually covered the AC-DC flyback converter principle. How does it operate? And how do we run it in the DCM mode? And with the DCM mode, how is the emulated resistance looks like? And and briefly, we have seen the waveforms, which are important. And we also use a filter so that the current waveforms at the input become sinusoidal. And at the end, we took a design example of the LED driver where we saw some of the important values and how to design those components, along with a little bit of touching upon, we have touched briefly upon the control system for this. Okay, so with this, we conclude the AC-DC flyback converter operation. Thank you.